acyl amino. Who is there? Okay. So by cyclation of two acyl amino toluenes using strong base such as sodamide or potassium tertiary butoxide in the absence of air at high temperature of around 200 degrees Celsius, so indole will be formed. Thus, the synthesis was limited to indoles such as 2-methyl indoles and to those substituents which were not affected by such conditions. So, sodamide. So, to acyl aminotoluene, we have again here toluene, acyl aminotoluene using sodamide cyclation takes place. Later, the use of butyl lithium as the base facilitated the reaction to be feasible at room temperature. So if you take N-butyl lithium, so temperature can be reduced to 20, minus 22 room temperature. But in case of sodamide, it requires high temperature or elevated temperature. Next is your Nenis-Chesu synthesis. It involves the conjugate addition of benzoquinone to a vinyl logos primary or secondary amide or beta amino protonic derivative or ethyl beta amino protonate. The product of this addition leads to the indole. So benzoquinone and vinyl logos primary or secondary amine. Vinyl group is there. So primary or secondary amine, primary or secondary amide. So cyclation takes place, substituted indole will be formed. In the research synthesis, here we have to take a compound which is having active methylene group. The activated methyl group of nitrotoluene on acylation with diethyl oxalate initiates the reaction. Further, reduction of nitro group and cyclation yields the final product as indole 2 carboxylic ester. You get indole 2 carboxylic ester. Finally, upon hydrolysis, the decarboxylation yields indole. So the double bond is missing, so it will be there. It will not be removed. Double bond is there. Then about the reaction, it undergo electrophilic substitution reaction. Electrophilic attack at C3. At C3 prefers in indole as compared to C2. Okay, why? Because this is more electronegative nitrogen, so obviously this will be moved, this double bond will move towards nitrogen, so here the carbocation will be formed. So 3 C3 is preferred in comparison to C2. You can see the stability of the carbocation if we check here. So when electrophile will attack, so two things will be there. Either carbocation will form at C3 or it will form at C2. So when it will form at C2, this nitrogen will not take part when it will form the C3. But when the carbocation will form at C2, then this nitrogen will take part in the bond, the lone pair will take part in the bond formation, providing a N plus here. At nitrogen will be positive, but nitrogen is more electronegative, so positive charge on more electronegative atom is leading to instability. You can see here, you can see that the carbocation obtained by attack of electrophile at C2 is not able to further stabilize by resonance, whereas formed by attack at C3 can be stabilized by delocalization of electron nearby n atom. So here the resonance stabilization is more, so electrophile can attack to C3, not to C2. So now the individual reactions, nitration, so definitely everything it will occur at C3 position. So nitration of indole can be done using benzoyl nitrate, which is a non-acidic nitrating agent yielding to 3-nitroindole. Benzoyl nitrate C6H5CONO3 or ONO2. So we'll get 3-nitroindole at 0 degrees Celsius. If nitration is done using usual nitrating mixture containing nitric acid and concentrated sulfuric acid, acid catalyzed polymerization occurs, leading to a complex product. So we cannot take the usual nitrating mixture, that is mixture of concentrated nitric acid and concentrated sulfuric acid. Rather, we have to take here benzoyl benzoyl nitrate or nitration. Then halogenation, three haloindoles such as 3-bromo or 3-iodo-indoles being unstable should be used immediately after preparation. These are unstable, but they can be prepared taking bromine in pyridine at 0 degrees Celsius or iodine in DMF and potassium hydroxide. So iodination and chlorination is usually done in alkaline medium. As in chlorination, initially N chloroproduct is formed which get rearranged to 3 chloroproduct. 2-bromo and 3-iodoindoles can be prepared by alpha lithiation, about which we'll study later on. Then sulfonation. So SO3 will be substituted at 3 position. Acylation. Acylation is possible both at C3 and nitrogen atom of the indole. So N-acetyl indole can be prepared using acetic anhydride and sodium acetate. Whereas trifluoroacetic anhydride, when used in DMF, it gives C3 acylated indole, while N-acetyl product results when the reaction is carried out in presence of sodium acetate and 4-dimethyl aminopyridine. Acylation and also alkylation, same at 3 position. There methyl iodide and DMF when you take, then at carbon atom methyl group is substituted. But after substitution of 2 and 3 position, if we are giving more and more methyl iodide, then it will be substituted at nitrogen. Okay, so indoles do not show any reaction with alkyl halide at room temperature. However, at higher temperature, 80 degrees Celsius, methylation of indole can be carried out to give 3-methyl indole. Thus, 3 substituted indole on 2 alkylation by cationic reagent yielding symmetrical spirocyclic intermediate. So that is spirocyclic intermediate will form, which leads to 1,2,3,4 tetrahydrocarbazole. Then Wilsmere reaction. 3-formyl indoles can be prepared by this reaction. So indole reacts with NN-dimethyl formamide and POCl3, phosphorus oxychloride. So 3-formyl indoles. Result, similarly, this compound also reacts with the indole according to the following mechanism, producing again 3-formyl indole. Then moving toward the Manning's reaction, the reaction of indole with a mixture of formaldehyde and dimethylamine under neutral condition and at low temperature gives N substituted product. So the N substituted product get converted to 3 substituted product, gramine, which is thermodynamically more stable in the presence of acetic acid or in neutral condition. Hello, what happened? Pramodini.
Sorry, sir.
So the N substituted product later on converted to the carbon substituted product, that is gramine. So the N substituted product gets converted to 3 substituted product, gramine, which is thermodynamically more stable in the presence of acetic acid or in neutral condition at higher temperature. However, gramine can be directly also prepared by performing the reaction in acetic acid. This gramine and its quaternary salt are important synthetic intermediate. The synthesis of tryptophan from gramine is given here. You can see gramine we have taken, and then diethyl acetamido malonate, malonic ester, malonate. So in presence of toluene as a solvent gives this compound, which often can be converted to by decarboxylation, converted to tryptophan. Similar to above, the dimethyl amino group of gramine can also be displaced by reaction with other nucleophiles such as cyanide, as shown here. So it will be converted to CH2CN, alpha alkylidine indolinine. Then moving towards oxidation. Oxidative cleavage results at 2,3 double bond. So cleavage will take place. By oxidation, this double bond will cleave, producing ketone. A variety of reagents such as ozone, oxygen in presence of cuprous chloride, sodium periodate, etc. can be used as the oxidizing agent. So sodium periodate we have taken here, aqueous methanol at room temperature. This double bond will cleave, producing the bicarbonyl compound. So 3 substituted indoles can be oxidized to oxindoles using DMSO, dimethyl sulfoxide, and an acid, DMSO and HCl, 0 degree Celsius. Then it will be oxidized to oxindoles. That means here one ketone group will be added. So two conditions are there. If you are giving sodium perchlorate or periodate, then you are getting a diketone or dicarbonyl compound. The double bond will break and 2 oxygen will be inserted. But in presence of DMSO, 3 substituted indoles. So in presence of DMSO can be just give oxindoles. Here one ketone group will be carbonyl group. This C group will be converted to a carbonyl group. The reduction, when nucleophilic reducing agents such as lithium aluminum hydride, sodium borohydride are used, indole is not reduced. But when liquid lithium in liquid ammonia is used, we get a mixture of products as shown here. So completely here two double bond is there in this benzene nucleus, but here one double bond is there. So the product ratio will be 20 is to 80. 20 this one, 80 this one. So the reduction of ring containing nitrogen is achieved either with sodium cyanoborohydrin or with triethylsilane in tetrafluoroacetic acid. But when you are taking lithium aluminum hydride or sodium borohydride, the benzene nucleus is hydrogenated, either dihydrogenated or tetrahydrogenated. But when you are taking sodium cyanoborohydrin in a triethyl with triethylsilane in tetrafluoroacetic acid, then the nitrogen ring, the ring containing nitrogen, get reduced. Then, if you are doing catalytic reduction, then both benzene and the 5-member ring, all everything will be reduced. The catalytic reduction of indole first produce indolene, and finally the completely saturated product. First this one indolene, the nitrogen containing 5-member ring will be saturated, then benzene nucleus will be saturated, giving a fully saturated product. This is the catalytic reduction. That means if you take hydrogen gas over palladium hydroxide, so three reducing conditions are there. If you are taking lithium in liquid ammonia, then we'll get a mixture of product which is either dihydro, benzene nucleus will be reduced, dihydro or tetrahydro product. But we are taking sodium cyanoborohydride or triethylsilane and trifluoroacetic acid, the nitrogen containing 5-member ring will be hydrogenated. But when you're taking the catalyst or hydrogenation, direct hydrogen gas in presence of catalyst like palladium hydroxide, then both the 6-member ring and 5-member ring contain nitrogen, everything will be reduced or saturated. Reaction with carbines, the indole anion attack the dichlorocarbene electrophile to yield a 3-dichloromethyl indole. So carbene, dichlorocarbene we have taken CCl2. So again, free radical, sorry, electrophilic substitution. So what will happen? So here it will be CCl2 minus. So then this intermediate will be formed, then converting to 3-formyl indole. As 3 the dichloromethyl indole will be formed, which upon hydrolysis gives 3-formyl indole. Reaction with the bases, the hydrogen atom at nitrogen of indole is quite acidic, and we get indolyl anion by the reaction of indole with strong bases such as sodium hydride, N-butyl lithium or alkyl magnesium halide. So this will be removed and Na plus will be attached. So that's why it will react with base sodium hydride or alkyl magnesium iodide, green acid reagent. So MgI will be attached here or Na plus will be attached here. If the N atom of the indole is substituted, for example, in N-methyl indole or with any other group, which may also assist substitution at 2 position, H at C2 is deprotonated and is shown in the following reaction. This is deprotonated at 2, it will be deprotonated, so lithium will be attached, rest thing is there, so it will form a bond like this. In reaction with Michael acceptors, 3 substituted products are obtained when indole reacts with alpha beta unsaturated ketone. Alpha beta unsaturated ketones are known as Michael acceptors. Alpha beta unsaturated ketone, nitriles and nitro compounds under acidic condition. nitro and alpha beta unsaturated ketone or alpha beta unsaturated nitro or nitrile. So will react to produce the following types of compounds. So this is about all about the reaction of indole. Now moving towards the benzofuran synthesis and reactions of benzofuran. So this is the structure of benzofuran. It is also known as furan or benzofuran. Okay. So in some natural occurring or synthetic compounds, benzofuran moiety is also present. This is used as a antifungal, anti-inflammatory, anti-tumor, anti-allergic drugs which contain benzofuran. So these are also some drugs which are used for treatment of variety of diseases. Amiodarone, so it is antiarrhythmic. Soralen, so which is used for treatment of psoriasis and vitiligo. So this one, xanthotoxin, notacanin, which is used for skin disease, vitiligo, atopic dermatitis, and also psoriasis. Angelicin, similar to soralen, which is used in the treatment of psoriasis, vitiligo, and human neuroblastoma cancer. So these are some drugs. Here also some more examples are there, which contains benzofuran nucleus. Now we move toward the synthesis. First one by vapor phase dehydrogenation and cyclization of 2-ethyl phenol. Vapor phase dehydrogenation. So at elevated temperature, this vapor will undergo dehydrogenation and cyclization of takes place. Cyclization reaction provides easier route than electrophilic substitution of parent heterocycle. Therefore, we can synthesize 2-acetyl benzofuran from 2-hydroxybenzaldehyde. So 2-hydroxybenzaldehyde, and we are giving here 1 chloroacetone and potassium hydroxide. So what will happen is OH, so Cl HCl will be removed. So OCH2 COCH3. So when cyclization takes place, this CH2, so here, so CH2 CH double bond here and COCH3. So 2-acetyl benzofuran will be the product. Similarly, 3-ethyl 3-ethynyl phenol, 3-ethynyl or acetylene 3-ethynyl phenol can be cyclized to give substituted benzofuran. See double bond, this will be converted to 1. So 1, 2, 1, 2, and R will be attached. So here, in case of palladium chloride or cupric chloride and sodium acetate, so the substituted benzofuran will be formed. Unsubstituted benzofuran can be prepared from bromoacetaldehyde, acetal or bromoacetal by using following sequence of reaction: ethyl alcohol, para-toluene sulfonyl hydroxide. So when reacts, bromoacetaldehyde acetal will be formed, which again reacts with phenol, producing this compound. Then cyclization takes place, forming benzofuran. Then acid catalyzed ring closure of 2 aryl oxyketone. This one I have taken, it is not aryl. So aryl 2 aryl oxyketone gives 3 substituted benzofuran, and that of 2 aryl oxy acetyl chloride is 3 oxygenated benzofuran, and here 3 substituted ketone. Then from 2 orthohydroxyl acetaldehyde or ketones or acids, by just here whether it is hydroxyaryl acetaldehyde or ketone or acid, whatever may be, so there will be dehydrogenation. So here, and double bond shift hydrogen removed, so H2O will be removed. So cyclic dehydration yields benzofuran as shown above. Then palladium catalyzed coupling of enol ethers. Then from ortho acyl aryl oxyacetic acid, acyl aryl oxyacetic acid. So these are the methods how the benzofuran will be formed. Then moving towards the reactions of benzofuran. The aromatic 5-member ring is cleaved readily by oxidizing and reducing agents. Lewis acid and concentrated mineral acids polymerize benzofuran, and the electrophilic substitution preferentially takes place at C2. Here, in case of the earlier one, indole, it was at C3, but in case of benzofuran, it will be at C2. So, first reaction, Bills-Mayer-Hack reaction with phosphoryl chloride or phosphorus oxychloride and DMF upon hydrolysis, that will be converted to benzofuran formaldehyde. Upon nitration, that is also occurs at C2 position. Here you have to give nitric acid and acetic acid, not sulfuric acid. So, but 3-nitrobenzofuran is also obtained as a major product on reaction with N2O4 in benzene. But when you're using nitric acid and acetic acid, we'll get 2-nitrobenzofuran. But substitution at 3 position occurs when you have to take dinitrogen tetroxide in benzene. Reaction with halogens, it form initially 2-3 addition product results, which on base promoted elimination of hydrogen halide yields a 3-halobenzofuran. So formation of 2-lithiobenzofuran, if you take 2-bromobenzofuran, react with N-butyl lithium, then that will be converted to 2-lithiobenzofuran or further treatment with carbon dioxide, so we will get the carboxylic acid. 2-benzofuran carboxylic acid. Similarly, if 3-bromobenzofuran is there, when it reacts with butyl lithium, so it also gives 3-lithium derivative, which can be converted to 3-carboxylic acid upon reaction with carbon dioxide. So 3-lithiobenzofuran undergo fragmentation. So there will be cleavage of the double bond, producing at room temperature to give a 2-hydroxyphenyl acetylene. 2-hydroxyphenyl acetylene will be formed. The furan ring, it will be cleaved. Then the last one, the double 2-member ring, that is the benzothiophene. So here the oxygen atom of benzofuran is substituted by sulfur, so gives benzothiophene. Two types of benzothiophene: benzo B thiophene, benzo C thiophene, or isobenzothiophene. These are some compounds containing benzothiophene moiety or nucleus, which are having medicinal value. Okay, which are used as for osteoporosis, insulin receptor activator, antibacterial, okay, anti-asthmatic. Synthesis of benzothiophene has been using 2-aryl thio or 2-aryl oxyaldehydes, ketones or acids. There you have used 2-oxy, aryl oxy, but here 2-aryl oxyaldehyde, ketone or acid, and also 2-aryl thio. So cyclization of the above compound via intramolecular electrophilic attack on the aromatic ring, followed by loss of water, generates the heterocyclic ring. Okay, to prepare the unsubstituted benzothiazine, an aryl thioacetaldehyde acetal is generally prepared. For example, thiophenol and bromoacetaldehyde acetal yield the aryl thioacetaldehyde acetal. Aryl thioacetaldehyde acetal, so when it reacts producing benzothiophene. The final step involves the cyclization of acid catalyzing closure. The ring closure of two aryl thioketones and two aryl thioacetyl chlorides yield three substituted benzothiophene. Then from aryl to chloroprop to enyl sulfide to chloroprop to enyl sulfide, when reacts with N-dimethyl benzene, N-dimethyl aniline, when it is heated, it will produce this intermediate, which upon heating with concentrated HCl produce the desired compound, that is benzothiophene, substituted benzothiophene. Then from ortho aryl thioacetic acid, esters or ketones, intramolecular aldol or Perkin type condensation takes place, producing the thiophene, benzothiophene. Taking the reactions of benzothiophene, it undergo electrophilic substitution reaction. The three position of benzothiophene is more reactive than two position towards electrophile. Benzothiophene is less regioselective than indole. Then the three substituted products are predominant products. However, other substituted products are also formed. Nitration. So here we can take the nitric acid. In case of benzofuran, we have taken nitric acid and acetic acid mixture. We can take here simply nitric acid. So the nitration in acetic acid, that more than 50% of 3-nitro derivative, however 2-nitro, 4-nitro, 6-nitro and 7-nitrobenzothiophene are also formed to extent of about 10% each. So in bromine, there will be bromination at three position, and also to give formaldehyde formylation will be there, we get methyl chloride. Okay. or chloromethyl, 3-chloromethyl benzothiophene. So this is a mixture of nitro compound for nitration. You can see here. Two nitro products is also obtained. Then halogenation, regarding chlorination. Controlled chlorination gives the following chlorinated compound: 3-chloro, 2-chloro, and mixture of and 2,3-dichloro. In the ratio, you can see the percentage: 3-chloro is 64%, 2-chloro only 3%, whereas 2,3-dichloro will get 28%. If excess chlorine is used, then 2,3-dichloro product is obtained. Regarding bromination, control bromination gives 3-bromobenzothiophene, about 9 to 2% yield, but when excess of bromine is used, 2,3-dibromobenzothiophene is also obtained, high, high yield. But iodination, as iodine is less reactive, in presence of mercuric oxide, it gave 3-iodobenzothiophene regioselectively. Formylation and acylation. Dimethyl formamide, or when reacts with acyl chloride in presence of aluminum chloride, it gives 3-acyl benzothiophene, and there also we'll get 3-formyl benzothiophene. Just 1 minute. Okay. Then regarding sulfonation, when reacts with sulfuric acid in acetic anhydride, we get a mixture of 3 and 2 benzothiophene sulfonic acid, and 3 position 92% yield and 2 position only 80%. But when we are using 70% sulfuric acid and temperature is 80 degree, we will get only the 3 benzothiophene sulfuric acid, sulfonic acid. Then on chloromethylation, we have to use formaldehyde and HCl. So chloromethyl group will substituted. So it yields 3-chloro monomethyl benzothiophene. At 3 positions, substitution occurs. Then with marine salts, marine salt is nothing, it is mix, mixture of silver fluorophosphate, hexafluorophosphate, and ClCS2, CS2Cl means dichloroethylene. So ring extension takes place. So the reaction is more powerful alkylating agent such as marine salt. Then oxidation, at sulfur there will be oxidation, so sulfoxide will be formed of sulfone. So benzothiophene 1,1 dioxide or sulfone will be formed, or 1,1 dioxo 2,3 dihydro. Upon reduction, it will be converted to thionaphthane. So when we are using the phenyl group, then or with xylene, then ring extension takes place, forming this type of compound. The oxidation of benzothiophene with MCBPA gives benzothiophene 1 oxide. So different oxidized products. Similarly, reduction also takes place. So this will be hydrogenated in presence of palladium sulfide and alumina, or whatever this reducing agent will take, will get the same product 2,3-dihydrobenzothiophene. So when we are using sodium in liquid ammonia, it yields 2-ethyl thiophenol. So it will be CS2 CS2. The ring will break and we will get 2-ethyl thiophenol. Metallation reaction with N-butyl lithium. So at two positions, lithium will be attached. Lithiation of benzothiophene using N-butyl lithium in tetrahydrofuran at minus 78 degrees Celsius gives 2-lithiobenzothiophenane, benzothiophene 2-ill lithium. So these lithium derivatives can further react to produce carboxylic acid or formaldehyde or aldehyde also. So benzothiophene 2 carboxylic acid when it reacts with carbon dioxide, when reacts with diethyl ether in presence of N-methyl and phenyl formamide, it gives 2-formyl benzothiophene. Cycloaddition reaction forming three-membered ring, three rings. So cycloaddition product across 2-3 bond. This one is shown producing this type of compounds. So this is all about uh, benzothiophene. You can go through these things. Some terminal questions also there with answer. Then we'll move to unit 6. 5-membered heterocycles with 2 or more heteroatoms in the ring. So we'll have a 5 minutes break. Then we'll start. Okay, shall start. The five-member Unit 6. The five-member heterocyclics with two or more heteroatoms in the ring. Here we will discuss the synthesis and reaction of benzimidazole, then benzotriazole and purine. Three compounds: benzimidazole, benzotriazole, and purine. So first one, the benzimidazole. So benzimidazole consists of an imidazole nucleus fused with benzene ring. So this one, benzimidazole is in the tautomeric form. You can see so many benzimidazole based compounds are also known, which is having antimicrobial, antiviral, anti-cancer, anti-diabetic activities. So now moving towards the synthesis of benzimidazole. So using orthophenyl phenylenediamine diamine and substituted aldehyde. So upon oxidation forms this one. Then reaction of alkyl or aryl heterocyclic acyl chloride and orthophenylenediamine, acyl chloride, aryl or alkyl, and orthodiamine, phenyl diamine. So upon cycloaddition, sorry, cyclodehydration gives the benzimidazole. Then from orthonitroarylamine will be formed when reacts with benzyl alcohol. So orthonitroarylamines reacts with substituted alcohol or amines by using reducing agents or redox reagents such as ferric chloride to give benzimidazole. Various paths are given here: aromatic amine, substituted alcohol or substituted amine. So when orthonitroarylamine, so producing the benzimidazole substituted, or simply you can, it also reacts with anyway to propanol. Then using ortho-substituted arylamines and aldehydes or ethyl acetoacetate. From N-arylamine in one pot, multi-component reaction enables the transformation of commercial arylamines, aldehydes, and azides into benzimidazole structural unit via efficient copper catalyzed amination of N-aryl imines. So this is a step. Then preparation of 2-aryl benzimidazole. So now moving towards the reaction. So both 1-alkyl and 1,3-dialkyl benzimidazole can be prepared. So when reacts with alkyl halide at 90 to 100 degrees Celsius, it gives one both alkyl and 1,3. So at nitrogen, hydrogen will be substituted. So we'll get one alkyl, which NH hydrogen will be substituted. Then on vigorous condition, if you increase the temperature, so giving the nitronium ion or imidazolium, benzimidazolium ion will be formed. The acylation reaction is also very commonly observed with benzimidazoles upon action with acid chloride and anhydride. So reaction with acrylonitrile. So when acrylation takes place, so N-cyanoethyl 1H benzimidazole will be formed. Here CH2 CN converted here. The nitrogen, the group will be attached. Oxygen, with oxygen, ethylene oxide will form, so 2-hydroxyethyl 1H benzimidazole will be formed. Reaction with alkali metal, so potassium salt will be formed. Alkali metal salt will be formed, which upon reacts with N-sulfonic acid, pyridinium N-sulfonic acid, so we'll get the sulfonic acid derivative. With formaldehyde, also we'll get hydroxymethyl benzimidazole substitution at nitrogen. So these are the reactions of benzimidazole. So now we'll move to the benz-triazole containing 3 nitrogen in the ring. So 1H benz-triazole, this is 2H means second hydrogen is there, or double bond is like this. So 1H and 2H benz-triazole has a ring system with 3 nitrogen atom which is fused with a benzene ring. So benz-triazole exhibit a wide variety of biological activities such as antibacterial, antifungal, antiviral, anti-inflammatory, anti-allergic, antioxidant. All these things are there. So these are the some drugs which contains benz-triazole. So moving towards the synthesis, by reaction of orthophenylidene diamine and nitrous acid. So sodium nitrate acetic acid produces nitrous acid. When nitrous acid reacts with orthophenylene diamine, so gives this intermediate, which upon removal of H plus produces the benzimidazole. Sorry, benzotriazole. The mechanism is this one. Then by 1,3 dipolar cyclo addition of azide and arines, ortho elimination of ortho trimethylsilyl aryl triplates by fluoride promoted reaction leads to arines. These arines on cycloaddition with azide yield substituted benzotriazole. Then from anthranilic acid, alkyl nitrite yields benzene. So benzene in situ, which reacts with anthranilic acid in situ. So benzotriazole will be formed. Substituted benzotriazole will be formed. Then N-alkylated benzotriazoles, 1H benzotriazole on methylation with different methylating agents such as methyl sulfate, diazomethane, and methyl halide gives a mixture of 1-methyl and 2-methyl benzotriazole in the ratio 5:17. So then from 1,3 dihydrobenzimidazole 2-ONE, so treated sodium nitrate gives the sodium salt of benzotriazole. So upon acid hydrolysis produces benzotriazole. Ring formation of benzotriazine. So benzotriazine 2H, so 1-ONE. So upon reaction with chloramine in DCM or lead acetate gives rise to benzotriazole substituted here. Then oxidative ring closure, 1-acetylamino 2-hydrazino 3-nitrobenzene when reacts with chlorine in presence of ethyl alcohol as a solvent gives 1,4-nitro 1S benzotriazole. There are some other reactions from 2-chloroaniline, from 2-amino azobenzene, from nitrobenzene. So by different route, you can see benzotriazole can be prepared. Regarding the reaction, it exhibits nitration, halogenation, then phenyl isocyanate, it also reacts, amination, sulfonation, alkylation. So nitration, so as these nitrogens cannot be nitrated here, so it will nitrate at the benzene nucleus. So 4 nitroderivatives results when benzotriazole is nitrated with concentrated nitric acid and sulfuric acid at room temperature. Will get 4-nitro benzotriazole. So this nucleus, the 5-membered ring cannot be nitrated because all are saturated. Halogenation, and nitration at nitrogen cannot happen. It only happen on the benzene nucleus, but halogenation can do at the nitrogen. One hydrogen is there in nitrogen, so it will be replaced by chlorine. So one benzotriazole is obtained when 1S benzotriazole is reacted with sodium hypohalide in aqueous acetic acid. It reacts with sodium hypohalide, then only halogenation takes place. Similarly, methylation, if it reacts with methyl iodide, so at N methylation occurs. Then with aquaresia, what will happen? Chlorination will occur in the benzene nucleus. 4, 5, 6, 7 tetrachloroderivative will be formed. So when reacts with azomethane, so there will be isomerization to second position. So methyl group will attach to the second nitrogen atom and will get 2 methyl 4, 5, 6, 7 tetrachloro 2H benzotriazole. Here it is 1 methyl, here it will be 2 methyl. With phenyl isocyanate, it will react producing 1 phenyl carbamoyl benzotriazole. Amination, a mixture of both N amino product is obtained on treatment with hydroxyl amine O sulfonic acid in hot aqueous potassium hydroxide. Then N-substituted benzotriazole is also obtained on reaction of trifluoromethane, sulfonic anhydride in dry-DCM and dry-pyridine. Alkylation also takes place at the nitrogen atom when alkyl halide and sodium hydroxide or sodium ethoxide is used. Then arylation also can be done with carbonyl compounds, with aldehyde or ketone. So it will give the addition product converted to hydroxyl derivative. So one hydroxyalkyl benzotriazole will form. When with ketone in presence of dialkyl amine, so what will happen? This amine group will be attached there. So one dialkyl aminoalkyl benzotriazole will form. If alpha beta unsaturated ketone, then the unsaturation point it will be attached there. So we'll get this type of compound. So other uses of benzotriazole. Benzotriazole and its derivatives have been widely used as corrosion inhibitor for copper and its alloys in the atmosphere and underwater. It forms a coating or a passive layer on the metal surface. It also used as an anti-fogging agent and as UV light stabilizers. Benzotriazole is water soluble and does not degrade readily, therefore, it is likely to reach the water bodies despite some treatment at the wastewater plants. It is it has low toxicity, but awareness about its presence as an environmental pollutant is important. Now moving towards the purine. You can see the structure containing four nitrogen atoms, a six-membered and a five-membered ring. The word purine was coined by German chemist Emil Fischer in 1884 from pure urine. Two important purines are adenine and guanine, which are the bases present in nucleosides and nucleotides. The structure of adenine and guanine. Some purine-based molecules of importance as given here as anti-cancer, immunosuppressive, caffeine, antiviral drug. So now moving toward the synthesis. Fischer synthesis. Emil Fischer synthesized purine in 1998 from uric acid. The scheme of reaction is given here. Uric acid, the keto form, reacts with phosphorus pentachloride, producing the chloro derivative. At the two ketone, they are converted to chloro. Then with HI, converted to iodo. When reduced with zinc, gives the purine. The keto or indole form, whatever, so gives the purine. By heating formamide, Formamide upon heating cyclizes or polymerizes, giving purine. Traub's method. In this method, 4,5 diamino pyrimidines, they can be prepared by introduction of amino group into 5 position of 4 amino 6 hydroxy or 4,6 diamino pyrimidines by nitration followed by reduction with ammonium sulfide. The ring closure is then performed using formic acid or chlorocarbonic ester. The sequence of reaction is given here and the mechanism also here. Then from imidazole with formamide, so gives 6 amino purine. Then the reaction of purine according to the delocalization of electron shown in the structure. You can see the position 2, 6 and 8. 2, 6 and 8. Just in between the nitrogen atom. 2, 6 and 8 are positive charge. So electrophile can attack. Sorry, nucleophile can attack. Whereas the position 3, 7, the 3 and 7 in one structure. Yes, here and here you can see they are negative or electron rich, hence they are susceptible to attack by nucleophiles. Protonation. The protonation means purine on reaction with acid involve protonation at nitrogen atom. So, you can see since there are 4 nitrogen atoms, protonation is possible at any of these nitrogens, but predominant product is the protonation at N1. Alkylation reacts with methyl iodide, so 7,9 dimethyl purinium iodide will be formed. Then electrophilic aromatic substitution reaction with nitration takes place at this 8 substituted product. Nitration can be carried out with a mixture of nitric acid and sulfuric acid. And about the nucleophilic substitution, that is electrophilic aromatic substitution, nucleophilic substitution, sodium ethoxide, so chlorine, purine having halo substituent undergo nucleophilic substitution reaction as these halides are good leaving groups here, so OC2H5 will substituted here. N-oxide formation reaction with hydrogen peroxide producing N-oxide derivative of purine. So this is all about purine or the heterocyclics with more than one ring. And okay, so next class we'll discuss the rest chapters, that is benzofuse 6-member ring with more than one heteroatoms. Okay, so thank you.